So I hope, I guess everybody here can hear me. So we can begin today's Boeing lecture colloquium, distinguished colloquium. Thanks to Dr. Fonseca, Irene, for accepting to giving the talk for us today. She's an extremely accomplished applied mathematician. She's a professor in Carnegie Mellon University and also director for Center of Nonlinear Analysis at CMU. She has been, very briefly, let me mention some of her accomplishments. She is a fellow of European Academy of Science and American Mathematical Society. She's a science fellow and has been a past president of science. She has published 2 books, one in calculus of variations and more recently. And her interests are mainly on, I'm saying it in terms of the physical applications, has been in elasticity and physics of materials, more modern subjects, and mostly focused on developing new techniques and mathematical foundations. But memory alloys, composite materials, magnetic materials, thin structures are really exotic subjects in elasticity. Another interest of is very related to the same thing, is phase transition fluids and solids. It's a very general subject in modern physics, and also in engineering and computer science, imaging and image processing. That's another field that she's been actively working on. So I won't talk much. I give it now Irene, we can begin the talk. I hope see if people are still joining.
So,
okay.
for the introduction, and I'm very thankful for being here today. It's a wonderful opportunity. Maybe in the future there could be I can visit you in person. So as Cameron was saying, yes, I have interests in materials or problems in analysis that are motivated by questions in material science, and that's going to be the topic of today. I also work in variational methods for computer vision, but that's not going to be the topic of today. So that it's going to be a completely different subject, a completely different topic. So I will talk about phase separation in heterogeneous media. It's a program that has been going on for quite a while, and I'm going to in here. I'm just mentioning some of my more current collaborators in the last few years. That are basically either current or past trainees, and so I'm going to start from the beginning. I think that for some of you, this is very familiar. So, and I apologize if it gets a little boring in the beginning, but I just want to set up the stage. So we're going to talk about the van der Waals model for phase transitions. And you have to, but I'm going to make it relatively simple in that you imagine that you have a container. And inside a container, you're going to have 2 phases. So your fluid wants to live in 2 phases. And that's depicted through an energy. You will be the phase field for your fluid. Omega is the container. W is the potential energy. And the fact that the fluid likes to live in 2 phases, it's basically translated in the fact that W has 2 wells, in this case, say at -1 and 1. And so we like to think that nature likes to minimize energy. Therefore, to be in equilibrium, you'd be where you can have the least energy, in this case, energy 0. To have energy 0, that means that you are either at this well or at that well. And usually there's some mechanism that prevents you from being all the time in one well or in the other. And it could be, for example, that the volume fraction, that the average of U is fixed to be somewhere in the spinodal region. So you are forced to have pockets of minor ones and pockets of ones. That's a prototype, say something like this, but it does not have to be. By the way, the first part of my talk is all going to be quasi-static, so there will be no evolution. And in that case, actually, my W can go from Rn into Rd. So these are vector value problems. When I do the dynamics, so when I will do the phase flow, then it's going to be for real valued fields. So as I said, omega is a container, U is the density of the fluid. Let's fix that. I want a fixed mass, so I want to have a fixed proportion of, say, one phase and of the other. So normally to be, say, that would have zeros, not necessarily minus 1 and 1, could be an A and a B. And you want to minimize them, this energy subject to this fixed mass. Now, of course, let's normalize. Let's assume that the container has volume 1, otherwise just average out. And again, M, it's going to be between the two L's, A and B. And so, you know, any U that takes just those values, A and B, on a set which satisfies the right measure so that the volumes that the average of V is M, and it's a simple back of the envelope computation, you find out that, okay, so then the measure of V needs to be this number, fine. So any field like that would have average 0. So you have tremendous non-uniqueness, right? You can have tons of different designs in your, right? I mean, any E that would look like these, but it could also have lots of pockets of E's inside. And so you have many different designs which give you always the same energy, 0. So the question is, well, is there a mechanism per which you can select a preferred minimizer among all these designs? And so this goes back to Hilliard, which they said, well, okay, so why don't we penalize surface energy? So every time that I go, say, from say a -1 here to a 1 there, I go across an interface and I pay energy. Here I'm paying surface energy, all these inclusions. So maybe there's a way of penalizing that. And one way to penalize that is to say, well, okay, so my U is not going to be piecewise affine. It's going to be smoother, like double F, basically continues across. And when I go across this interface, then I pay with the gradient, right? So here the gradient is 0, the gradient is 0. But when I go across, I pay with the gradient. And so this is basically surface energy. So if the width of the transition layer is epsilon, so if you have like something like this, where so you go from -1 to 1, right? So this would be the transition layer of width epsilon. So that is exactly of order 1, and this is basically of order 1. So it goes to 0, you don't see much. And in order to see something, you should then divide by epsilon, because all this is basically like a bigger of epsilon. You divide by epsilon, and what you're going to see something of order 1. So I epsilon is the one that basically is going to go to 0. I scale that, right, like so. I put it F epsilon. Now there's something of order 1, and the question that you ask in terms of types of variations is, okay, let epsilon is a small parameter, it's that width of the transition layer. So let epsilon go to 0, and what is the effective energy that I get in the end? Can I characterize what is this effective energy? And if I do, will this effective energy actually select among all those minimizers I had in the beginning, will it select a particular one? So it turns out that, yes, indeed. So again, we had phases A and B. If you look at there where U is equal to Y, let's call it A0. And so it's going to be a theorem. That's, I'm going to take it next. That the effective energy up to a constant, which is explicitly calculated here in terms of the potential energy, it's the perimeter, it's the surface area inside omega of a 0. So this is your container omega, say that is A0 is this, and say A0 is that. And what you count is, and so this is phase, say, so you have phase, so this is A, and that's B here. And what you count, this perimeter inside omega counts these. It does not count the container, and it would count that. So it would be this surface area plus that surface area is that perimeter, which is the same as the perimeter inside of omega of the other phase. They are exactly the same, right? Say this phase weight is equal to y or equal to b, it's exactly the same. Okay, so let me very briefly with one slide remind you what is the notion of convergence between functionals, right? We have an energy f epsilon which converges to an energy f. What do I mean by convergence of functionals? And the notion we use here is the notion of gamma convergence. And there are two parts to the gamma convergence. So we say that f epsilon gamma converges to an f if on one hand you have this what we call the gamma limitive property. That is, every time they approach u by a sequence u epsilon, the effective energy of u is below the limitive of the energies. And you cannot do better, it's tight, in that I can find what it's called a recovery sequence. The recovery sequence is a sequence that actually converges to u and gives you the opposite inequality. So between these two, you actually get an equality for the recovery sequence. It's exactly there. So you don't have a gate, so it's not too low. You actually can attain exactly this f of u with a particular sequence that recovers the effective energy. And a very important property of gamma convergence, so this goes back to the school of the Giorgi in Italy in the 50s and the 60s. And an important property is that when f epsilon gamma converges to f, global minimizers of f epsilon converge to global minimizers of f. And the interesting thing is that f epsilon usually it's more regular, right? Because remember, f is going to admit functions which have jumps, while f epsilon, I have gradients there, so these are smooth functions. So minimize of f epsilon, I can do our Lagrange equations, right? I can find PDEs, I can track what these u epsilons, the minimizers for this one satisfy in terms of the PD, I can do a lot of work there. And then I know that these minimizers do converge to particular minimizers of this target. So remember, this was the original energy. Well, this was the original energy. Then I perturb it with a little bit of a gradient. And by the way, this can be much more general than what I'm mentioning here. For example, you could have higher order derivatives here. You could have dependence on position. This could actually be coupled. You could have something that looks like, say, an f of u epsilon grad u. And for example, my colleague and friend Guy Bouchité had worked on coupled models. So it can be much, much more general. But I'm giving you essentially the prototype for this. So Girton, who's, by the way, a colleague of mine, Martin Girton conjectured that again, as I announced before, that minimizers of these of the original energy of this energy actually converge to a particular one among all those designs. Remember that I called U with an E, that means that inside E you have one phase, outside E you have another phase, so it's a piecewise constant function. And he said, you know, it's going to select a particular one which is going to minimize surface area. Among all these designs, we want to serve in surface area. So among all these possible designs here which satisfy the right constraints, so that you have the right volume, I prefer the one that minimizes area. Okay, now again, if you just leave it like this, you don't see much because it goes to 0. We divide by epsilon. Now this is going to be of order 1. And it's okay in terms of minimizers because dividing by epsilon, I'm not messing up minimizers. Minimizers of these are the same as minimizers of that, right? The minimizers of I epsilon and of f epsilon are exactly the same, right? So that's fine. Okay, and so that's a theorem. Goes back to Modica, Mortal, Stenberg, and then I did it This was all for real scalar valid, and then with Luke Tartar we did from Rn to Rd, so completely vector valid. And okay, so we proved this vigorously that indeed these functions converge to basically the perimeter of the phase where u is equal to y inside omega, same as the perimeter as u is equal to b inside omega, times a constant. That's, and you can look at this constant as an isotropic surface energy density. So I can write this. Another way of writing this is writing the integral over the boundary there where u is equal to a of this constant times, say, surface measure, right? But it's a constant. So you factor that out, and what you get here is the perimeter of this boundary, right? So, and as I said, the constant is explicitly calculated this way. And I want to stress this because this is what we call, it's called isotropic surface energy, in that the surface energy density does not depend on the normal to the interface, right? So you have that interface here where u is equal to a. You have a normal to the interface because the function is bounded variation. So you have the notion of perimeter is well defined, the notion of normal is well defined. And in this case, it does not depend on the normal. So it's just surface area times the constant. So next, what I want to do is, well, okay, so now suppose that when that the mixture that I want at every point in the container depends on where I am. So suppose that, for example, near the boundary, I want mostly phase A, and inside and near the core, I want a very, very, very fine mixture of phase A and phase B. So that means that now my one way of translating that into the model is that now my surface, my potential energy, it's going, okay, it's still going to be zero depending on P is this value, where P is equal A or B, but it depends on position. And delta epsilon is a parameter that goes to zero very fast. It goes to zero as epsilon. And so you're going to get, and the faster it goes on position X, you're mixing more and more A and B faster and faster, right? Faster and faster, although there's no time in here, but in terms of microstructure, you're mixing them more and more. Okay, so I'm going to assume these are now, you may ask me, oh, wait a second, but then why should the Waals now depend on position? Maybe when I sit at position X, this should be an A of X and a B of X. Good point, I'll come back to that later on. But let me first talk about the case where the potential is always zero on A and B, and I'm making this very high oscillation here, so it's going to be an homogenization problem. We should not, in principle, ask in terms of regularity with respect to this variable. Oh, by the way, it's going to be periodic here. Q is the unit cube in our n oriented according to the orthonormal basis. And so basically you have a W that has some shape there, and then you just take copies of that and you pave all the space with copies of that cube. So that's cube periodicity, right? And in terms of the regularity with respect to this very fast variable, you should not ask for more than measurability, because what you have in mind is that on the cube, which again, then I just tiled the whole space with that cube, you'd like to have one spot, say E, where you have an energy W1, and on the complement, you should have an energy W2. But you see, if I do that, then in terms of dependence on position, it's only measurable, right? Because it jumps from W1 to W2, right? And again, I'm going to refer to that later on. So at this time, at this point, when I just do quasi-static, no dependence on time, no evolution, that's all fine. We can do just measurable with respect to X, to position, and then periodic in U. There are things that you can do in this field for like almost periodic. As far as I know, the full stochastic homogenization has not been done yet for this model, although of course it's in our bucket list. What is the goal? The goal again is, okay, so if I have this family of energies, if I let epsilon go to 0, what is the effective energy? And so what is the selection criteria that this gives me? So what are the kind of designs that I would be selecting in the end of this exercise? As far as I know, there were 2 previous works along these lines, one in 2003, the other one in 2009, one by Sidney Brides Piat, but a little different because the fast variable, the homogenization, it's not on the W, but it's in here. So instead of having the Dirichlet integral, they considered an f of quadratic here in grad U, but they did homogenization here. That makes it the problem very different, because here you're going to have a competition, because on one hand, you want to have W equal to 0 with the periodicity that is conformal with the periodicity of W, so with the periodicity of the unit cube, so along the orthonormal directions. But on the other hand, you're going to be sitting on normals to the interface that have nothing to do, that may have nothing to do with orthonormal directions. So you're going to have a competition here that you don't see there. So this is quite different from what we're doing here. And then there was some work by Brides and Catherine. Again, different. It's scalar to scalar, to R to R, and they did not scale by epsilon. So this, as you see, this is all, and they had a very particular family of energies. Ours is very general. So now, when you have a problem like that, the first question that you ask is, oh, okay, so I could have 3 regimes here, right? I could have delta epsilon going to 0 like epsilon. I could have delta epsilon going to 0 faster than epsilon. And I could have delta epsilon going to 0 slower than epsilon, right? So delta epsilon going to 0 faster than epsilon basically is that you first have an homogenization effect here, and then you go to a phase transition to an interface, to an interfacial energy. Epsilon going faster than delta epsilon is basically, oh, I first have like a can here with like I first go from bulk to interfacial energy, but I still have an homogenization effect happening there at the interface. I'll come back to that later. Right now, what I'm going to talk about is the regime where delta epsilon goes like epsilon. It doesn't have to be exactly like epsilon, although I'm going to take it like epsilon. But what you need to know is that basically that this limit, this goes to limit alpha, which is between 0 and infinity, right? So it's a regime. Okay. So I'm going to take it that they go in tandem. Okay. So so the result says that, okay, again, the limiting energy, and this should be a script F, is still going to be an interfacial energy, just as before, but you see that now it's an isotropic. There's before was a constant. I could CW that I factored out. Now you cannot. It's a constant. It depends on the normal to the interface. Now, this is very interesting because in most singular perturbation problems, like this one's that I know of, the anisotropy comes from the anisotropy that you build in the interfacial energy. So if instead of the Dirichlet integral, which is totally isotropic, does not see directions, if I had an f of grad U, I would likely get something which would be an isotropic. Normally, when you start with isotropic surface energy, because it's the higher order term, you expect to get an isotropic surface energy. Not in this case. There is this homogenization effect. It's going to actually percolate through the problem, and this is going to be anisotropic. We have what we call cell from, and by the way, we can prove that it's exactly anisotropic, and I'll come back to that. So it's not just that we cannot prove that it's isotropic. We can actually prove that it's anisotropic unless you are in trivial regimes. So let me guide you through the cell formulas. So basically what you do is this. You have your normal nu, maybe I have it here, it's in here. So suppose this is nu. So you're going to take a cube that I call Q nu, which has two faces centered at 0, has two faces perpendicular to nu. And then normally I would like in the limit to just see, say, face B on top and face A on the bottom. And if I blow up, right, on a point on a nice point of the interface, I blow up. I see basically a hyperplane tangent to the interface with the normal mu. And if I blow up, I'll see B on one side, A on the other. Okay. So that's basically what we're going to try to do here. So I say, okay, so I'm going to take that cube. I'm going to dilate it. T is going to go to infinity. I'm going to take larger and larger and larger cells. There has been an homogenization effect here, so no longer the scale has disappeared. And eventually, you're going to expect that it's going to go to surface energy. So everything is going to concentrate at the interface. So this is going to look not like bulk, like should be T to the N. It's going to look like T to the N minus 1, which is the area of the interface, right? So you're going to scale by the area of the interface. You're going to infimize over admissible U's, which I'm going to tell you what they are, and then you let these scales go to infinity. Basically, you get larger and larger. You're going to infimize over nice H1 Sobolev functions, and you'd like them to look like B and A, right? They have to be Sobolev, so they cannot be B and A because that has a jump. It's not Sobolev. So say, well, okay, fine. But seen from the outside, I would like to see a B from the outside. I'd like to see an A. Well, that's also not admissible, right? So it's not a trace of a nice H1 function. So what you do is you take what you'd like to look like and you modify. You modify. You take your favorite modifier, you modify it, now it's admissible. And actually, by the way, this does not depend on the choice of modifier. So why the anisotropy? So basically, if the normal is oriented with the direction of the producer of W, say En, then what you do is you look at the interface, you're going to take one of these cells, and then you're going to repeat them, right? But you tile your interface with these cubes, which are aligned with the productivity of W, right? And basically, you're going to just add them up. The energy that's captured in each one of them. But if the interface is skewed with respect to the orthonormal base of Rn, you are in trouble because the energy now is not the sum of the energy that is captured in each piece here on each cube. It's not the same. And so this is reflected by, I mean, this is, okay, hand-waving kind of argument. Of course, there is a rigorous argument, but that's basically what it is that you don't have an additive argument here, which, by the way, in terms of the Choksi variations, that's translated into what we call the Riemann-Lebesgue lemma. So, and I'll come back to that. So we had this family of energies F epsilon. We want to prove that they converge to this limiting energy F, which is the surface energy. What is the roadmap? But the roadmap, basically, it's pretty much the same for this kind of simple perturbation problems. You start by proving compactness. That means you start by proving that if you have a family of fields such that, say, the energies are uniformly bounded, that then you can prove that you can extract a subsequence which converges to some U, which may not be in the original. So these U epsilons were Sobolev, were H1. Your U is probably going to be BV. So, but it converges somewhere in some sense. Okay, so that's the first thing. Is that okay? So if I start with uniformly bounded in terms of energy fields, they converge in some sense. Okay, then remember that for the gamma limit, you have to prove two properties, the gamma limitif and the gamma limit sum. The gamma limitif is to say that every time I approach my U, my energy, my effective energy is always below the limitif. The gamma limit sup is the recovery sequence. It's to say that, oh, but by the way, I can actually attain it. I can actually produce, fabricate a sequence that gives me exactly the right thing. Usually, the gamma limitif is the hardest part of the proof because it's okay. So you try to go down and down and down, and you have to basically conjecture what is your limiting energy. Once you have it, finding the recovery sequence is not that hard because you can do that because by doing this exercise of going down, you kind of figure out what is the limiting energy. So then you kind of basically can do and produce by a blow-up argument, you can produce what is the recovery sequence. In this problem, it's exactly the other way around. We kind of figured pretty soon, we kind of figured what would be the limiting energy, but recovery sequence was complicated. So that's what I'm going to basically concentrate my my attention here. And again, the challenge is that in the intermediate layer, we have two competing phenomena. So the limiting field likes to be an A and a B. In between, we have both high oscillations competing with concentrations. The energy wants to concentrate to an interface, wants to get rid of bulk, but at some time you are oscillating like crazy in there. Okay. So I will not give you proofs, but I'm going to go very fast through a couple of slides, and then I'm going to zoom on one where I tell you why does this work for when the transition layers align with principal axis. So let's assume that, say that that the normal on a piece of your interface, you take a little point there. Now you're going to blow up, and what you see is basically something which looks like that when you blow up. And so let's assume that the normal is EM. And then you go back to the cell formula. And the cell formula tells you that, oh, this is actually a limit. Remember, there was the size of the cells were going to infinity. You average them out. And then you were minimizing with these fields that were good, right? It looked like a modification of B on top and a modification of A on the bottom. Let me call them UK. Okay, then you do some scaling because instead of having them living on these big cubes, you want to concentrate them near the interface. That's what I'm doing here. But okay, that's a long story. And you keep doing this stuff. The bottom line is that after you go through lots of scalings, and for those of you who are familiar with this homogenization techniques, is that at some point you get a double limit, and the point is that what goes first to zero is epsilon, so that's the first variable that goes to zero, and in epsilon you look at this, epsilon appears only here, it appears only there. This is your field V that is going to oscillate fast near the interface in the direction, in this direction. Z prime is the first n-1 coordinates. And W has the good taste of oscillate exactly with respect to the same. And W likes to oscillate on these ones because remember these are the directions of periodicity. So when you have that, you can use what is so-called the Riemann-Lebesgue lemma, which tells you that I can get rid of these limits and then recover this. That's a one-line proof. And then again, you undo your scaling and you go back to your sigma. So with this, I just produced, this would be then my recovery sequence, okay? this is very hand waving. It doesn't, if you're not familiar with Riemann-Lebesgue lemma, forget it. But basically, what I'm saying here is that when the normal to the interface is aligned to the direction of periodicity of W, then basically your recovery sequence is oscillating exactly in tandem as with W. And so you can get rid of these oscillations by using this lemma. Okay, now what happens if this is skewed? Okay, so the first interesting result, which is a result in linear algebra, which I learned very recently, was that the observation, not only your W is periodic with respect to the unit cube in Rn, but actually, if I take normals that live in this space, which are called capital lambda, and these are elements of the unit sphere whose coordinates are all rationals, then if I take very, very large cells, I now have that W is periodic with respect to these skewed cubes. And good news, this is actually dense on the sphere. I'm sure that all of you would believe me. Remarkably, this is a very recent result from 1980s or 1990s, that this is actually dense. It's linear algebra, but it is very recent. Okay, no, okay. I mean, I would think that this would be a result of the 18th century, but it's not. Okay, but you can say more actually, that if you take one of these normals that again live in this space, all rational coefficients, you can actually complement that with n-1 normals, all living in the same space, so that you get an orthonormal basis. And now you have W also periodic with respect to all of these. This is not your typical Gram-Schmidt theorem, because you need them to believe all in there. So there's a little bit of work. And there are all kinds of fun results that you can obtain. For example, if I again have one of these good normals, but if I have a rotation that maps En into this normal, I can find another rotation that in Euclidean distance is very close to the original one, but now maps all the other elements of the orthonormal basis into good normals, those good normals that are those that W likes. Okay, so then you prove properties of sigma. Sigma is well defined and it's finite. It does not depend on the Charles modifier. It's supersymmetric continuous. Actually, at the end of the day, you're going to get that sigma is going to be the energy density for a gamma limit. And so we know that it actually has to be convex. Therefore, it's going to be continuous. But that's an after the fact thing. Right now, you prove by hand that it's convex, and so on. And so then, okay, and then I'm not going to repeat, but then you're going to basically emulate what we did for the first case when it was when the normal was aligned with orthonormal basis in Rn with the canonical, and now you're going to tile, but now with these cubes that we just fabricated with these normals. How do you wrap up the problem? Well, look, if now I give you an arbitrary U, first, there's a density result for which you can approximate U by UNs for which their interfaces are polyhedral. You have convergence in L1. The perimeters of those polyhedrals converge to the perimeter of the interface of U, and even more. You can force that all these polyhedrals have normals in the good set. Oh, but if that's the case, then there is a result that goes back to the Reshetniak that says, oh, okay, but then with this type of convergence, I have, and if sigma is supersymmetric continuous, something that I proved by hand before, then I know that I can have this result. But now for each one of these, I know how to produce recovery sequence because now I have polyhedral sets with good normals. So each one of them, I can find a good recovery sequence. So then you have this, it's bounded by this, and in turn, this is bounded by that. So now you diagonalize and you get a good recovery sequence for your U. And that's it. So in the last 10 minutes, I want very, very fast to very briefly tell you about now gradient flows. Okay, so let's look at the L2 gradient flow for our energy. Disclaimer. By the way, there is already a paper that already actually was came out today in the Calvine PD. That's the first part of our work with Rustum, Choksi, Jessica Lin, and Raghav. And we do the gradient flow for this case. Several disclaimers. First, this is all for scalar values. Second, while in what I talked about now, W was a couple X over epsilon U, now it has to be decoupled. It's going to look like so. The oscillations are essentially decoupled from the concentrations. We don't know, and I'm not saying it's without loss of generality. That's the case we treated. Okay, that's it. More, we treated the case where W looks exactly like so. Of course, I believe that everything we did can be extended to this case, but we have not done it. So that's probably a PhD thesis in the making. So we didn't do it. Okay, so you're going to start, okay, so this is just the gradient flow. We're going to start with a well-prepared initial condition. In that is a very nice set of finite perimeter, and you go back and you know that you have a recovery sequence for that, right? So put it to epsilon. And on the parabolic boundary, I just put normal boundary conditions. Okay. When A is equal to 1, this is back to Alan Kahn. And many people have worked on that, and that's basically the model. Many people have worked on that in many different ways. So there are matched asymptotic techniques. Also, my colleague Bob Pego worked on that. That there's a classical PD approach, variational approach, viscosity solution approach, geometric measure theory approach, and that's the one that I'm going to concentrate is actually on this one. The upshot, though, is that in all these approaches, the answer was the same. Namely, U epsilon is going to converge to a U that solves basically motion by mean curvature, which is the normal velocity to the interface is proportional to the mean curvature to the interface. Except that with different approaches, you have different notions of weak solution. That's what it is. Okay, so again, so the homogenization dream is to know what the U epsilons go to what. What does U solve? Okay, I don't have a lot of time, but let me just briefly tell you. In the case where A is equal to 1, this is that's just your Lagrange equation. And what you do is that goes back to Monica Mortola, you seek for equipartition of energy. And that is given by basically a traveling wave by a hyperbolic tangent that looks like, so if you look at, this is essentially the Euclidean distance of the point to the interface that has normal mu, right, scaled by epsilon. Q is the hyperbolic tangent connecting one route to the other. So that would be the case minus 1, 1, right? So connecting with this hyperbolic tangent. Again, equipartition of energy. You solve the heteroclinic ODE. And it tells you that, oh, okay, in this case, if I plug this Q that looks like so, which is the hyperbolic tangent, into my energy, because I have a equipartition of energy, these and these are the same, so I can write them like so, right? Because they're exactly the same. But now this is a perfect derivative, and so that's exactly what I call, remember, it was that constant, CW, that I called in the beginning. So you see that it does not depend on the normal, it's always the same. It's just this constant. But now we have A that's not constant, right? That's the whole point. So you can have that's oscillating. And so you're going to say, well, okay, so let's do something here. And I'm going to, again, I have an Eikonal equation, but instead, before this was the Euclidean norm. So now I'm going to take a remaining metric that's adapted to the geodesic, right? So I'm going to take the distance between 2 points with the weight square root of A, which is just infinize of all curves that connect I1 to I2. And so if this is the hyperplane I'm trying to approach, I will do it with the sign distance. So I take the distance, this distance to the hyperplane, and it's the sign distance, right? Instead of being x dot nu, now it's going to be this distance. And if I call this h nu, well, I get what I expect. So that's going to be basically the Eikonal. And again, in the case where a was equal to 1, and in the case where this q was given by the hyperbolic tangent, that was exactly what we did. We take q composed with h dot nu, and we got exactly sigma. And you may ask, oh, maybe we can do the same, we can play the same game here. And so let me plug now, not this, right? No, not just z dot nu, but now this one instead of this. And maybe I get something which is also constant and therefore isotropic. And as I told you, no. The answer is no, unless A is constant. But if A is constant, you don't have an homogenization. And you're back to Allen-Kahn, to the classical Allen-Kahn. So that is a theorem that you can prove that unless A is constant, you cannot play the same game. And now you can prove though, that was the original sigma, you may recall. You can prove that actually instead of asking you to look like this boundary condition, you may want to ask you to look like what you'd like to look everywhere. That's okay, that can be done. So in particular, you always get one inequality, right? In the case where A is equal to 1, that's an equality. And you may ask, so I already have an inequality. Can I have an equality? That's a theorem that says that, well, this you already have that is below that. You'd have equality if lambda naught would be 0, right? Then the gamma limit if and the gamma limit could be the limit if and the limit could be the same. And you can prove that this is actually a real gap. That's actually strictly positive. So that's I don't want to bother you with that, but actually this is exactly equal. It's never 0, and actually this was proven by Feldman and Peter Morphy, who's a student of Takis Oganidis, now starting a postdoc in the summer. They first proved that when the normal was irrational components, this was different from 0, and then actually that was extended to any normal. So we know that it's never 0. So you do have a gap, and you don't have an isotropic energy. Okay, I'm reaching the end of my time. So let me just very briefly, again, remember this was this kind of signed weighted distance to the hyperplane. And this is, in homogenization, this is called the Planetmatic Problem, which is, can you characterize this limit as t goes to infinity? And indeed, and you can even go to almost periodic functions, you can prove that in the limit, and that's a local uniform convergence, in that every time I have k compact, actually this is a max, and when n goes to infinity, these converges to some constant depending on the normal, again anisotropic, and then basically looks like the distance to the hyperplane affected by this anisotropic constant. What is the big deal? So that's the way we're going to interpret this. So Monte Carlo and Minucci in 2003, they proved that every time that you fix a normal, and you look at this Planetmatic Problem, that that actually this is actually the unique viscosity solution to this problem in the upper half plane, while this is the unique viscosity solution to the pure Eikonal equation, again in the upper half plane. So what we proved here with these results there is that viscosity solutions to these PDEs actually converge. So these converge to PDEs, to the solution, converge locally uniformly to the viscosity solution. So we have a convergence of this problem to the pure Eikonal equation. There have been a little bit more work on that recently for Armstrong and Carnegie, and also Feldman and Sugarides and Feldman. But as far as we know, there are no other homogenization results for this planetmatic problem in the periodic setting, which is the one that we are dealing with. So open problems, well, there are many open problems. For example, you could think, well, what about more than, I talked about two phases, right? You could have multiple phases, okay? Of course, the problems become more complicated because then you have triple junctures, for example, you have three phases, but in the quasi-state, okay, disclaimer. In the case where you don't have homogenization effects and quasi-static, yes, it has been done and studied. Again, as I said, you could have here perturbations which, for example, put the Haitian, right? Why grad U? Maybe you want to have mean curvature effects, right? So things like that. What about, as I said, the bottom, the wells depending on X, right? Y should always be A and B. Well, that is something we are finishing that paper with a current PhD of mine and Riccardo Cristoferi, who was a former postdoc. So we are doing that where you have depending on position. And then there are the other regimes that I mentioned to you, right? Could be, suppose that epsilon goes to zero much faster. That means first you have the collapse of bulk into surface, but then you still have homogenization. As far as I know, nothing is known there. It's a very, very, very hard problem. And then you have the other regime, which is, oh, let's now have delta much less than epsilon. So first it homogenizes, basically, and then, although you cannot separate the two, but say, and then you have the phase transition. Until very recently, with my student, Adrian Hagerty, we knew how to do that, but there was a gap. We could only knew how to do it if epsilon was really, I mean, there was a gap between epsilon n over delta n going to infinity because you could only do it for faster than 3/2. We now think that we can, again, it's my student Venkatraman, who's graduating his May, who has a postdoc in Germany next year, and Riccardo Cristoferi. We now think that we can actually do these. Oh, okay, actually very interesting. If you don't have an homogenization effect, if the wells don't move, we know how to close this gap, and we can do it for power 1, just faster than delta epsilon, that's all. But if the wells move, it seems that this does appear there. So, but okay, we are still thinking about it. It's not written, so maybe it's wishful thinking at this point. Okay, so thank you very much for your attention. I think this is a good place to stop. Thank you.
Thank you very much. So we have a little bit time for some questions. So if anybody has questions, please just ask directly. I have a couple of questions myself, but let's other ask first, please. Please just ask, yes.
Yeah.
Sorry, let me unmute. Thank you very much for your talk. I had a question, you know, the free energy that you drew with the, symmetric wells. I'm assuming that all of these interfacial energy and anisotropy findings would extend into the case where you would have, sort of non-uniform wells, like a conserved order parameter.
Absolutely. So in quasi-static regime, it's very general. Okay. All I ask is that W grows at least linearly at infinity, and it's zero at exactly 2 points. I don't care even if it's quadratic near the wells.
Okay.
It's very, very, very general. All I ask is that it grows at least linearly at infinity, and it's zero at exactly 2 points. That's all I ask. But in what I've talked about now, the gradient flow.
Yeah.
What we did, it's very specific for 1 minus u squared because we did a lot of calculations with the exact form of the traveling wave. It's a hyperbolic tangent, then you have a hyperbolic sequence, and then you have errors that look like exponentials. And it's very, very tailored to that. That being said, I believe that it can be generalized to much more, to a broader family of energies. In the quasi-steady case, yeah, it's very, very general. You ask very little from them. It doesn't have to look like that. It can be very general. And it can even have more than 2 wells.
Other questions?
I was going to say that it's late, but it's late here. It's not late there.
So I have one. It's about like applications exactly. These are. I guess we can apply it. Can we apply the first part of the first half of the talk? These things on liquid interfaces, like more like percolation related problems, like oil droplets on a water surface.
Oh yeah, and it has been done.
And these, I know they have been done, yes. And
yeah, I mean, I'm not directly involved in that.
Yes, you are proving the homogenization techniques rather, yeah.
Absolutely, yes, yeah.
It's very interesting. And
Can I ask an analysis question?
Please.
Or Cameron, are you still asking?
No, I'm done, please.
Okay. The result where you were able to extend to almost periodic functions, that's a really messy space of functions to work with. Are there any specific analysis problems that show up?
Well, okay, so the reason why we did that was because eventually we want to actually do this in the stochastic framework, right? Like Armstrong and Neumann and others are working. And then of course have quantitative results for error estimates and stuff like that. So we are just trying to push to the case of stochastic homogenization where it's not deterministic. And that was basically a first step. But it's not that we are particularly interested in almost periodic. It's just that it does not have to be that deterministic. It does not have to be exactly periodic. We have a little bit of room, right, in the almost periodic. And if actually we want to put some noise in there and do this in the random context, they're not there yet. But that was the reason why.
But there were no complications that showed up because you're not dealing with a non-separable space or anything like that?
No, it works well. No.
Okay.
It's a messy space. It was fine.
Okay.
Actually, it gave us hope that actually we can push this further.
Right.
Yeah.
And may I ask some small question as well? Just these are. I have one more question. May I ask?
Sure.
These are probably just more general elasticity questions. In other contexts, when there are free energies, like in physics context, we have superconductivity, and many other examples. You have Kosterlitz-Thales transition. When you have a vortex solution, when the energy is plainly dominant by the surface energies, so you prefer to have.
Yeah, but it's talking more like it's Landau, or right?
Exactly, but in your case, you don't have we have to have some external gauge field or some type in these things to do have.
But it's an interesting question, and again, you could also think about homogenization in that context. But no, there's nothing in Ginsburg lambda.
But in elasticity, what the external gauge field mean? Do you know? I know they do these things, but it's a different meaning.
Yeah, I don't know.
Thanks. But in these cases, we don't. We just get the phase boundaries solutions and those, and we don't get any vortex solution. Of course, yeah.
No defects appearing. It's just
And any amazing boundary solutions come from the heterogeneities in the system, I guess. Yeah. Okay, if there are no questions, we can finish. And I thanks again, Irene, for an amazing talk and beautiful subjects.
For hosting me virtually. So it was a fun night. Thank you.
Thank you so much.
Bye-bye.
Bye-bye.